Hello viewers, welcome back to this channel. So in this video we are going to be finalizing thermochemistry. So in this video we are going to be handling the ending parts that we had already started under thermochemistry. So this video is presented to you by Algembe. So if you advise, subscribe to the channel and share the video to your friends so that you can all benefit as a family. So you're going to be proceeding with solubility over any compounds in water. Now any compounds are the same as salts for as long as you have a metal, for example sodium, combining with a non-metal, for example a chlorine atom. So if sodium and chlorine react, they form sodium chloride. And such metals, combination of a metal and a non-metal, we call such compounds ionic compounds or salts or electrolytes. So we are going to be looking at the solubility and the factors that determine the solubility of such compounds in water under thermochemistry. So we're going to start by saying that for any ionic compound or any ionic salt to dissolve in water in order to form a solution, there are two energy changes that are going to be involved. And the two energy changes are going to determine what we call enthalpy of the solution. So the enthalpy of the solution depends on two factors or two energy changes, and one is going to be Lattice energy and the other is going to be hydration energy. So whenever you see any question telling you to describe the factors affecting enthalpy of solution, are going to be Lattice energy and the other one is going to be hydration energy. So starting with lattice energy, we are going to be saying that ionic lattices are the same as structures. You can call a lattice a structure. So ionic lattices are going to arise as a result of electrostatic forces of attraction that are between the positive and negative ions present in a specific compound. And then the measure of the strength of the lattice is going to be given by the lattice energy. Remember in the previous video we defined what we call lattice energy. So here we are going to be looking at lattice energy, and I say that lattice energy is both ways. We have lattice energy in terms of formation, which was the first video, the second video that we had, where we drew energy level diagrams and we had to determine lattice energy. Now that is lattice energy in terms of formation, energy is given out. But in solution, we are dissolving this compound so that we get its ions. So in other words, we are breaking the bond between the ionic lattice, and here lattice energy is going to be positive. So you have to pay attention to that closely. So you're going to say that lattice energy is going to be the enthalpy change that occurs when 1 mole of a crystal lattice is broken into its constituent gaseous ions. Now we are defining lattice energy in this case in terms of bond breaking, and therefore the enthalpy or the enthalpy of the lattice energy when you're dealing with enthalpy of solution is going to be positive, and it's going to be positive indicating that the process is endothermic. So we can also define lattice energy in terms of the second video that we are looking at in terms of bond formation. So lattice energy in terms of bond formation is going to be the enthalpy change which occurs when 1 mole of an ionic crystal lattice is formed from its constituent gaseous ions. Now notice that these ones are gaseous ions, they are not any other atoms, not atoms. Majority of you or majority of the students have a habit of mistaking gaseous and they replace it with atoms. They are gaseous ions, not atoms. So in terms of bond formation, it's going to be that energy change or energy evolved, because when you're forming the bond, we are giving off energy to the environment. So it's going to be the energy evolved when 1 mole of a crystal lattice is formed from its constituent gaseous ions. But when we are dealing with enthalpies of solution, we are looking at dissolving an ionic crystal lattice. So we are looking at breaking the bond so that we give off the constituent gaseous ions. Now since it's breaking the bond, that means that it's going to be the energy required. So to define lattice energy is going to be the energy required when 1 mole of a crystal lattice is broken down into its constituent gaseous ions. So you have to pay close attention to that. Now we are going to make a note and say that lattice energy is going to be a good indication of the strength of the ionic bonds. The higher the magnitude of the lattice energy, the stronger the ionic bond that is going to be formed. So this one otherwise means that if at all we have our lattice energy being very high, like for example in the energy level diagrams that we drew in the second video, that means that the bonds that are formed between that element are going to be strong. So in terms of bond formation, the more negative our value of lattice energy is, the more stronger the ionic bonds that are present within that ionic salt or within that ionic compound. So you're going to be saying that the reason is because more energy is going to be released when strong bonds are formed, and at the same time more energy is required to break such bonds. So in case you're having, from U.A.C.E's law or from U.A.C.E's diagram or from your energy level diagrams, in case you're having a more negative value, that means that when you come to enthalpy of solution, when you're dissolving that salt, the more negative value is going to be again more positive, because equal amount of energy that is released when bonds are formed is the same amount of energy required to break those bonds when you're dealing with enthalpy of solution. And we say that in solution, lattice energy is in terms of bond breaking, because the compound has to be dissolved or broken down into its constituent gaseous ions, which requires energy. So the more negative the lattice energy is from the S diagram, the more positive it's going to be when you're dealing with enthalpies of solution. And the reason for that is because more energy, more magnitude, equal and opposite magnitude of energy is going to be required to break such bonds, so that we release the various gaseous components that are present in such a compound. Now you're going to be saying that lattice energies are important in the following ways. So one, they are going to help us determine the magnitude of melting and boiling points of any ionic electrolyte or any ionic compound. So like we said, that the more negative that energy is, the more energy required to break such bonds. And therefore, since melting and boiling points are explained in that way, that means that they can easily help us to determine the extent of the melting and boiling points of specific compounds. And we are going to be looking at this in the next video under structure and bonding. So you're seeing that also they help us to determine the solubility of ionic salts that are present in water, in addition to the hydration energies of the ions. So usually we determine solubility of ionic salts. Explain whenever I see any question about explaining solubility of any salt that has been given to you, we explain it in terms of lattice energy and hydration energy, as we are going to be seeing in the further examples. So if at all lattice energy is greater than hydration energy, remember that in solution I told you lattice energy is positive. Hydration energy in solution is going to be negative. So in solution, if hydration energy is greater than lattice energy, that means that there is more negative. The value is going to be more negative at the end, and therefore such a salt can easily dissolve in water. But if the lattice energy is more than the hydration energy, that salt is assumed to be sparingly soluble in water. Since the lattice energy is more positive, it will be assumed that there will be more energy required to break such a compound into its constituent ions, and therefore it cannot easily dissolve in solution. So that's it. So if lattice energy is greater than hydration energy, the salt is less soluble in water or is sparingly soluble. But if hydration energy is greater than lattice energy, the salt is going to be more soluble in solution. And we explain solubility in terms of lattice energy together with hydration energy. So you have to pay attention to that and understand it very well. Going to the Roman number 3, we are going to say that lattice energies are also important in connection with chemical calculations that are involving in Born-Haber cycles. And we looked at this more in details in the second video. So let's look at the factors affecting lattice energy. Now lattice energy and hydration energy are going to be affected by the same factors, and there are only two factors where we are having ionic charge together with ionic radius. We explain lattice energy and hydration energy in terms of only two factors: ionic charge and hydration energy, or ionic charge and ionic radius. So let's start with the charge on the ion or the ionic charge. So we're going to be saying that lattice energy is going to increase with increase in the ionic charge. This is because increase in ionic charge increases electrostatic forces of attraction between the oppositely charged ions. So the greater the extent of the ionic charges on the cations and anions, the stronger the lattice energy. The reason is the higher the magnitude of the charge present on any ion and on the cation, the stronger the forces of attraction that comes into these contacts. Just like we said, unlike charges attract one another. So the larger the magnitude of the charges, the stronger the attraction, and hence the higher the lattice energy, or the higher the energy required to break such a compound into its constituent gaseous ions, which we termed as lattice energy. So lattice energy is going to be increasing with increase of the ionic charge. Reason being, as we increase charges, oppositely charged charges, we increase forces of attraction between them, and therefore such bonds are not easily broken, since there are higher forces of attraction between the oppositely charged ions, and therefore they are going to be increasing lattice energy. So for that example, we are going to be considering an example between magnesium chloride and sodium chloride. Now notice that in magnesium chloride and sodium chloride, anions are the same. But what you're going to notice is that magnesium and sodium, or the cations, are going to vary. And the charge on the sodium ion here is positive 1. The charge on the magnesium ion in magnesium chloride is positive 2. So we expect lattice energy to be greater in magnesium chloride as compared to sodium chloride. And the reason is because of this. So you're going to be saying that magnesium chloride has a higher lattice energy as compared to sodium chloride. Reason being, the electrostatic forces of attraction between the magnesium ions and the chloride ions are greater than that between the sodium ions and the chloride ions. Reason for the variation in the magnitude of the charge that is present on the cation. As we say that the higher the magnitude of the charge, the higher the lattice energy. And the lower the magnitude of the charge, the lower the lattice energy. So let's look at another factor, which is going to be ionic radius. So under ionic radius, you're going to be saying that lattice energy is going to increase with a decrease in ionic radius. And the reason for that is, the smaller the ionic radius, the closer the oppositely charged ions to each other, and therefore the stronger the ionic bond. So we expect that if at all the ionic radii for the two different atoms that are present in the ionic salt, the smaller they are, the closer the oppositely charged charges, or the closer they are going to be. In other words, the bond length is going to be short. And you say that if the bond length is short, that means that it's very strong. So the lower the ionic radius, or the smaller the ionic radius, the higher the lattice energy. Reason being, the opposite charged ions are going to be very close to one another, forming short bonds that are very difficult to break, and hence strengthening the lattice energy. So also going to continue by saying that also charge density increases with decrease in ionic radius, and we are going to be explaining this one more in details in the next video, which is about structure and bonding. So also charge density increases with a decrease in ionic radius, and the higher the charge density, the stronger the electrostatic forces of attraction between the oppositely charged ions. For example, if you're having sodium chloride, we assume that sodium chloride has a higher energy than potassium chloride. Reason being, if you compare the two, both sodium ion and potassium ion, you'll find that both of them are group 1 elements, or they are ions from group 1 elements. But if you look at their ionic radii, you assume that, or we shall determine, or you will see from the periodic table, that the sodium ion has a lower or a more smaller ionic radius as compared to potassium ion. And therefore, we expect that the bonds that are present in sodium chloride are going to be very short and strong, and therefore increasing lattice energy as compared to the bonds that are present between the potassium ions and the chloride ions. And therefore, sodium chloride has to have a higher lattice energy as compared to potassium chloride, due to a bigger ionic radius that is present in potassium ion as compared to that in sodium ion. So proceeding, let's look at the part B part of it. So we have looked at lattice energy, so we're going to look at hydration And another name for hydration is going to be called solvation. So it can either be called hydration energy or solvation energy. So we're going to define hydration energy or solvation energy in the following terms, and I'm going to be saying that hydration energy is always going to be the heat given out. Always avoid this word, enthalpy change. So hydration energy is going to be the heat given out when 1 mole of a gaseous ion is surrounded by water molecules to form an infinite dilute solution. Now you can proceed by saying without changing pH. You can continue this statement by saying without a change in pH. So you're saying that it's going to be the heat given out when 1 mole of the gaseous ion is surrounded by enough sufficient water molecules to form an infinite dilute solution without a change in pH. And the reason for that is because all this is going to come about by is the Lattice energy that first takes place. Lattice energy is going to help us to dissolve anionic salt, for example magnesium chloride. Lattice energy in enthalpy of solution help us to break the bonds between it so that we can get the gaseous ions. So what hydration energy does, or what hydration does, is that we get these gaseous ions, we surround them with sufficient water molecules so that we can convert them to aqueous ions. And by converting them to aqueous ions, we are forming an infinite dilute solution that happens without changing pH, because both of the ions that are present are both surrounded by sufficient water molecules to give us the respective ions that are present in aqueous solution, that is assumed to be at infinite dilution together without changing pH. So hydration energy is always exothermic, or is always the energy given out. But Lattice energy is both exothermic and endothermic, and Lattice energy is only exothermic when you are forming a bond. But when you are dissolving a salt in a solution, Lattice energy value turns to a positive. And you are going to have that very common, or you are going to see such examples very common. For example, in your papers, in part B, you may be required to draw an energy level diagram or a Born-Haber cycle, and then in part C, we shall give you enthalpy of solution. But then you are required to turn the negative that was present on your Lattice energy, you convert it into a positive when you are dealing with part C, because in part C will be dealing with enthalpy of solution. And in enthalpy of solution, Lattice energy must be endothermic. It must be energy required, since it involves breaking a bond present in an ionic compound to give the constituent gaseous ions. It's only hydration energy when you're calculating for enthalpy of solution. It's only hydration energy or solvation energy that is negatively charged. And Lattice energy when you're calculating for enthalpy of solution is always positively charged. So let's look at the factors that are affecting hydration energy. So factor number 1, you're going to be looking at the charge of the ion, or what you can call as the ionic charge. And similarly, just like in the previous explanations, we are going to be saying that hydration energy is going to increase with the charge on the ion. Reason being, highly charged ions are going to have high charge density, and therefore they are going to strongly attract many water molecules around them. And as a result, this is going to increase a lot of energy, or is going to release a lot of energy. The higher the charge that is present on the ion, the more strongly they attract water molecules present in that solution, and therefore the more they attract these water molecules, the more they become hydrated, the more energy is released. And since hydration energy is energy released or heat given out, that's why we are going to be saying that hydration energy is therefore going to be increasing with increase on the charge of the ion. Since they always become heavily hydrated in solution, or the higher the magnitude of the charge present on the ion, the more stronger it attracts water molecules towards itself, and therefore the more hydration is going to release. So if you are to compare a salt of magnesium ions and a salt of sodium ions, we are going to see that the salt of magnesium ions is going to have the highest hydration energy as compared to the salt of sodium ion. Reason being, in magnesium ions, the magnesium ion has a higher magnitude of a charge as compared to the sodium ion. We say that also in hydration energy, there are the same factors that are affected just like Lattice energy. ionic charge and ionic radius. So let's look at the factor of ionic radius. So here we are going to be saying that an ion with a small ionic radius is highly hydrated as compared to an ion with a big ionic radius. To put this in details, or to make it more understandable, is that hydration energy is going to be increasing with a decrease in ionic radius. Reason being, when you're having a small ionic radius, we expect the nuclear attraction to be stronger. And once the nuclear attraction is stronger, that means that water molecules are going to be attracted towards that ion as quickly and as easily as possible. And in that case, or in the process, such ion with a small ionic radius is going to be heavily hydrated in solution. And the more hydrated it becomes, the more energy is released in the solution. And with that, we conclude that ions with a smaller ionic radius are going to have higher hydration energy as compared to ions with a larger ionic radius. So if we are to compare lithium and sodium, we are going to see that lithium is going to have a higher hydration energy as compared to sodium, simply because lithium ion has a smaller ionic radius as compared to sodium ion. Now the mistake here that I want to quote on is that when you're explaining these terms, you forget, instead of writing ionic radius, and you write atomic radius. When you're dealing with ions, especially with this topic, you are going to be dealing with ions. When you're talking about ions, talk about ionic radius. When you're talking about atoms, talk about atomic radius. This mistake is also common among students who answer diagonal relationship questions. When you're talking about an atom, talk about atomic radius. When you're talking about an ion, talk about ionic radius. Now let's look at enthalpy of solution. Now in enthalpy of solution, like this is what I've been talking about. Enthalpy of solution combines both the hydration energy and the lattice energy. And we have said that in solution, lattice energy is always positive, but in solution, hydration energy is always negative. So we're going to be starting by saying that a solution is formed by dissolving a salt in a given solvent. And continuing, we are going to say that during the dissolution of a solid in any solvent, a certain amount of heat is going to either be absorbed or evolved. Now explaining this, just like I told you, enthalpy of solution is going to be given by the summation of lattice energy, which is always positive, and the hydration energy, which is always negative. So it is going to be absorbed in case the lattice energy is greater than the hydration energy, and it is going to be evolved in case the hydration energy is greater than the lattice energy. And we say that if at all the lattice energy is greater than the hydration energy, that salt is going to be spirally soluble in the solution. But if at all hydration energy is greater than lattice energy, we expect such a salt to be easily soluble in a solvent. So we're going to say that such heat changes are known as enthalpy of solution, and we're going to say that heat of solution or enthalpy of solution is usually defined for an infinite dilute solution, and we're going to define it in the following case. So enthalpy of solution is going to be the enthalpy change. It cannot either be heat evolved or released because we don't know the magnitude of lattice energy together with hydration energy. So we're just going to be using enthalpy change. So enthalpy of solution is going to be the enthalpy change when 1 mole of ionic solid or salt is dissolved in water to form an infinite dilute solution, such that no further dilution takes place. So that on further dilution, there is no heat change that takes place. So it's the enthalpy change. Key terms here are going to be enthalpy change when 1 mole of ionic solid or electrolyte is dissolved in sufficient amounts of water to form an infinite dilute solution, such that on further dilution, there is no further heat change that is going to take place. And this is the equation for dissolution of any ionic salt in water. Now this dissolution is not fully elaborative because the steps that are involved, in other words, this is the enthalpy of solution, but the steps that are involved in making this solid ionic compound into its aqueous gaseous ions is that we must first have lattice energy, and then from lattice energy the gaseous ions are hydrated to form what you call the aqueous ends, and you're going to be saying at how such things are related. So you're going to be saying that in the above equation, the dissolution of the ionic solid in water is going to be viewed as the following. So first, the crystal lattice is breaking down to form individual gaseous ends, and therefore, remember that we say that this is lattice energy. Breaking down an ionic crystal lattice into its constituent gaseous ends is energy required. So this process is going to be endothermic. And you're going to be saying that hydration of the oppositely charged gaseous ends is going to be an exothermic process, because we say that hydration energy is always negative. So the relationship between the lattice energy, hydration energy, and enthalpy of solution is going to be shown below. And let's look at it. And therefore, looking at the relationship, for example, if you're having sodium chloride, for sodium chloride to dissolve in solution to give us the aqueous ends, we are going to call the general or overall change or overall enthalpy to be called enthalpy of solution, because we are dissolving a salt into its aqueous ends. So the overall energy is called enthalpy of solution. But the energy changes that take place, or the individual processes that are taking place, is that we first split the ionic crystal lattice into its constituent gaseous ends. And there, this is an endothermic process because energy is required. And this is called lattice energy, just like we looked at it. So lattice energy helps us to break an ionic crystal lattice into its constituent gaseous ends. States are very important in thermochemistry, so you make sure that we elaborate them properly. So breaking the ionic crystal lattice into its constituent gaseous ends is the first step, and it's going to give us sodium ions in the gaseous state and also gaseous chloride ions. And then enthalpy of hydration converts our ions, each of them, into aqueous ions by simply surrounding them with adequate water molecules so that we can form an infinite dilute solution without changing pH. So hydration energy, what it does is that it's going to convert the chloride ions to aqueous chloride ions and also the sodium ions to aqueous sodium ions. And therefore, these are the two energies that are required to get what we call enthalpy of solution. So by Hess's law, we say that enthalpy of solution is going to be equal to lattice energy, which is always positive because it's always energy required. So that's why I told you, in part B, you'll be required to draw an energy level diagram. Now in part C, they'll talk about enthalpy of solution. But for you to answer enthalpy of solution very well is that you have to get this energy value from lattice energy that you got as a negative. For example, let's say you got negative 400. When you're calculating for enthalpy of solution, you come and say lattice energy is now going to become positive 400. Because in solution, lattice energy turns to endothermic. And the hydration energy for it is always negative. So you're going to make notes of the following, and you're going to say that for an ionic compound to easily dissolve in water, the lattice dissociation energy should be overcome by the hydration energy, such that the overall enthalpy of solution is going to be negative. Like I explained this earlier, if at all the lattice energy is less than the hydration energy, or the hydration energy is more negative than the lattice energy, then we expect the overall enthalpy of solution to be negative. And that means that such a solution is going to easily dissolve in water or in solution. But when the lattice dissociation enthalpy or energy is greater than the hydration energy, enthalpy of solution is going to be endothermic, or it's going to be positive. And therefore, for such salts that dissolve endothermically, their solubility is sparingly soluble in solution. And therefore, we are going to be saying that salts that dissolve endothermically, their solubility increases with increase in temperature. And therefore, at room temperature, such salts are going to be sparingly soluble. In other words, if lattice energy is greater than hydration energy, we expect that enthalpy of solution is going to be positive. And once you calculate your enthalpy of solution to be positive, the comment that you give is going to be that such a salt is not sparingly soluble in solution, or such a salt does not easily dissolve in water. And the reason for that is because the enthalpy of solution that you have calculated is going to be positive, or it's going to be endothermic. So proceeding, we are going to be saying that when the hydration energy is greater than the lattice dissociation enthalpy, enthalpy of solution is going to be exothermic, and for such salts, they are going to dissolve exothermically. Their solubility is going to decrease with an increase in temperature. In other words, for them, they are easily soluble at room temperature, just like we have just explained. So we're going to be saying that compounds which dissolve exothermically are more soluble than those ones which dissolve endothermically. I hope you know that already, just like I've already explained. Because for those ones that dissolve exothermically, we expect the hydration energy to be greater than their lattice energy. And it's when hydration energy becomes more negative than the positive lattice energy, then such salts are easily soluble at room temperature, as compared to those ones which have the enthalpies of solution to be endothermic. And when you're making comments, you say that such a salt is more soluble. If you calculate and you have an enthalpy of solution which is negative or which is exothermic, the comment that will be required in part D, you just say that that salt is easily soluble in water or is more soluble in solution. And the reason for that is because the enthalpy of solution is either exothermic or you say it's negative. So let's proceed to the given example. Now in this example, you are given the following thermochemical data for aluminium, fluorine, aluminium fluoride are given below. So Roman number 1, you are going to draw a Born-Haber cycle so that we can determine aluminium fluoride. Now remember that in energy level diagrams, you are forming a compound. In other words, the lattice energy that you are going to be calculating here is going to be for formation of a bond. But when you proceed to enthalpy of solution, we are going to get our answer to be negative. But when we proceed to the other part of enthalpy of solution, lattice energy is going to turn to positive. Reason being, in solution, we are breaking a bond of aluminium fluoride to aluminium ions and fluoride ions. So we covered energy level diagrams in the previous video, so I hope this one will be a quick turnover for you. So just like we covered these energy level diagrams in the previous video, I'm going to be as quick and brief as possible. So what you do is that we first write a balanced equation. So aluminium reacting with fluorine to give us 1 mole of a compound of aluminium fluoride. So balancing this equation, we put here 3/2. And then the other thing is that we ensure that every element is present in its standard state. That's the first thing you have to start with. And then later, you consider putting the energies. So we write the overall energy required for the enthalpy. Enthalpy of formation of aluminium fluoride was given as negative 1301 kilojoules per mole. So we write the energy changes just like we covered them in the previous video. So first of all is going to be sublimation or atomization of aluminium. The other one is going to be first ionization energy. The other one is going to be second ionization energy up to the third ionization energy. And then later we go to atomization of fluorine. But we are given bond dissociation energy, and we say that bond dissociation energy, to get atomization energy is the same as a half of the bond dissociation energy that was given. So we get bond dissociation energy which was given, we divide it by 2, and then we get the coefficient here, we multiply it by that energy, because we're having 3 atoms. And bond dissociation energy, if you have it, we're only going to get energy for 1 atom. So we get these 3 atoms that we have here, and you multiply the 3 by that, so that you can get the energy for all the 3 atoms. And then we undergo electron affinity to form the fluoride ion. Together here, we are having the electron affinity that was given was for 1 fluoride ion. So we get these 3 which is here, because we're having 3 fluoride ions, we multiply it by the energy for 1 fluoride ion, so that we can get the total energy that will be given off by the 3 fluoride ions. And then the other one is going to be Lattice energy. Lattice energy is when we get these gaseous ions to react. Its energy given out when the gaseous ions react to give us a bond. Now let's put that in details, or in terms of calculations according to S.'s law, so that you can get lattice energy, which is denoted by delta H L. So using the cycle that you have created in the previous board above, you are going to be saying that using the cycle you have drawn, determine the lattice energy of aluminium fluoride. And by S.'s law, we are going to say that enthalpy change for the overall reaction is going to be equal to the summation of all the enthalpy changes that have been involved in our diagram. Now notice that here I didn't include the positive charges on these values. Notice that for you when you're writing these values, you include them because we consider energy to be carrying a sign. And if you write them like this, that means that you're no longer writing energy values. So always put the signs and you bracket them. Also, this one is positive 79. So adding everything and making delta HL, which is our Lattice energy, the subject, you're going to get negative 5,945 kilojoules per mole as your Lattice energy. So when you're going to Roman number 3, that's where we're going to talk about enthalpy of solution. And here, you're going to be given with hydration energy. So you're going to say that, given that the hydration energies of aluminium ions and fluoride ions are the following: negative 4,690 and also negative 364 kilojoules per mole, respectively. That means that this value is for aluminium ions and the next value is going to be for fluoride ions. So calculate the enthalpy of solution of aluminium fluoride and comment on the solubility of the aluminium fluoride in water. So what you're going to note here is going to be 1. First is going to be the value of Lattice energy used in this part is going to be positive, even though in Roman number 2, which is where we have calculated it for, is negative. And the reason for that is because the Lattice energy in solution, when you're dealing with enthalpies of solution, the crystal lattice is being broken down to form its individual gaseous ions during the process of dissolution, and therefore Lattice energy here and the enthalpy of solution is considered to be an endothermic process. So in part 2, the value of Lattice energy is negative since 1 mole of a crystal lattice is being formed. So part 2 was for formation. All energy level diagrams are for formation. But when you're dealing with enthalpies of solution, we are going to be dealing with bond breaking, dissolving the salt to give us the constituent ions. So Lattice energy is going to turn to a positive. This is very important because this is the mistake majority of the students make under these calculations. So to form its constituent gaseous ions. So we write the formula for finding enthalpy of solution, and we say that enthalpy of solution is going to be given by delta H of the solution to be equal to Lattice energy, summation of Lattice energy and hydration energy. Now, summation Lattice energy or Lattice energy is going to turn to positive. Remember that in the part 2 it was negative. So here it's going to turn to positive, and I've said that I didn't include positive as I was typing, but make sure that you include them when you're writing your notes, when you're taking notes. Now, getting hydration energy is another factor that is going to affect your performance. This is where majority of students who have passed this, changing the sign of that, fail to get hydration energy or the proper value of hydration energy. For you to get hydration energy properly, you get what you're being given. For example, let me use aluminium chloride, though we use aluminium fluoride. So you get aluminium chloride, you first ionize it in solution, and if you ionize aluminium chloride in solution, you're going to get aluminium ions. Now notice that here, the coefficient of aluminium ions is going to be 1, but the coefficient of chloride ions, for it to balance the equation, is going to be 3 times the chloride ions. Now since the energy value that was given in the question was for 1 chloride ion, that's why you are seeing that we got the 3 which was present on the chloride ions that we get in solution, and we multiply it with the energy value for 1 chloride ion. So it's going to be 3 times negative 364. So that you can get the overall energy produced when you ionize chloride ions in water. And you can only see that when you write this equation. So always make sure that you include this equation whenever you are getting enthalpy of hydration. It's the only trick under enthalpy of solution. There are 2 tricks. This one for writing the equation of ionization so that you can see which coefficient should you multiply with, and also changing that energy that you have calculated from negative to positive, because in enthalpy of solution, Lattice energy is always positive. So here, after putting everything in the calculator, you're going to end up with positive 163 kilojoules per mole. And the comment here is going to be that the solubility of aluminium fluoride in water is going to increase with an increase in temperature, or aluminium fluoride is sparingly soluble in water, or you can give that. And the reason for that is because the enthalpy of solution is positive, or you can say the enthalpy of solution is endothermic. So you're going to note that most salts without water of crystallization, for example, anhydrous copper 2 sulfate, is going to dissolve more exothermically than those that have water of crystallization. For example, hydrated copper to sulfate. And the reason for that is because hydrated copper to sulfate is already having some component of water of crystallization in it, and therefore its Lattice energy is going to easily outweigh the hydration energy it's going to give in solution, and therefore is going to give an endothermic value, and therefore we expect hydrated copper to sulfate to be more sparingly soluble as compared to anhydrous copper to sulfate, which has no water of crystallization. Now let's look at the experimental determination of enthalpy of solution of any ionic compound. So let's look at the setup. So in the setup, we are going to have your apparatus arranged in this format. So what you're going to do is that you're going to have a smaller tube, and in this smaller tube, we are going to put our our ionic crystal lattice. And with our ionic crystal lattice, we are going to add water so that we can form what we call a solution. Now we are going to add this stirrer so that it can stir our solution or our ionic solid to easily dissolve in water so that we can form a uniform solution. And you're going to have a thermometer. Now the purpose of the thermometer is to record the maximum temperature that is attained. Note the word maximum, or you can use a steady temperature if you refer to write maximum. It is to note the steady or maximum temperature attained on dissolving. So first we record the temperature of water and without a salt, and the other one we add the salt and we stir, and we record the steady or maximum temperature attained. And then to control temperature or to control environmental effect is that we are supposed to seal. I forgot to stop at this apparatus. You are supposed to seal it so that no heat is given off to the surrounding. And after that, we put it in a calorimeter so that you can regulate the amount of heat from the surrounding and also given off to the surrounding. So it's acting as a temperature regulator. And then we put it in a bigger tube which is containing water, and this is purposely to prevent heat loss to the surrounding. The water is also, this tube is also given a stirrer so that we can easily prevent the environmental temperature from affecting our experiment. So let's look at the procedure that is going to be involved. So first, you put a known volume of water in a plastic beaker, and you note its initial temperature, which is going to be T1 degrees Celsius. And the second step, you're going to a known mass of an ionic solid, for example X grams, is going to be crushed and then it's going to be added to this water in the beaker. And as we're adding it, the mixture is stirred to form a solution, and we record the final steady temperature. I said this word is very important. The final steady temperature or the maximum temperature. So the final steady temperature or the highest or lowest temperature of the solution is going to be noted or recorded as T2 degrees Celsius. And therefore we are going to start treating our results as we recorded from the experiment. So by conversion, temperature change is going to be equal to initial temperature minus final temperature. So remember that initial temperature was T1 degrees Celsius and final temperature was T2 degrees Celsius. So change delta T is going to be equal to T1 minus T2 degrees Celsius. And then mass of water used, remember that we used a known volume of water. So for us to convert it into mass, we get density times volume. And density of water is 1, and the volume we used is V. So for us to get mass is given by density times volume. So we get the volume times the density so that we can get our mass as V grams. And then we are going to make an assumption that the solution was sufficient dilute, and also the specific capacity of the solution is going to be the same as the specific capacity of water, which is always 4.2 joule per gram per Kelvin. And we are going to assume that there was no heat loss or gain from the surrounding according to the experimental setup that we made. So we're going to be saying that heat change evolved or absorbed is given by mass of any component. But remember that the total mass for this solution is going to be mass of water plus mass of the solid or the ionic solid that we had. So to first get heat change of that compound of the solution is going to be equal to V plus X is going to be the total mass times the specific capacity, which is 4.2 times temperature change. Now since we are determining enthalpy of solution, we say that it must be given off by 1 mole of an ionic solid, heat given out or absorbed by 1 mole of an ionic crystal lattice. And remember that 1 mole is equal to molecular mass, which is denoted by this. So what we're going to do is that we used a given mass of X, or for us to get the moles that we used, for us to get the moles of the solid that we used to get this heat, is that we are going to get the given mass that we used, which was X of the solid, divided by its molecular mass. So these moles of the salt caused a heat change of this. And then what about 1 mole? Because we want heat evolved by 1 mole. That is what we call enthalpy of solution. Then what about 1 mole? So we shall divide this expression by this term, and it's going to be this. And further simplifying it is going to be in terms of joules. Further simplifying it, you are going to get this. Or someone can easily convert this MR and remain with X in the denominator. You take MR up, which is the molecular mass. So enthalpy of solution is going to be equal to, it is the enthalpy change. It can either be positive or negative, joules per mole. Or for us to convert this joules per mole, we divide through by 1000 so that we remain with this expression. And this expression is what is going to give us enthalpy of solution. So looking at enthalpy of solution neutralization, or going to the next topic, which is going to be enthalpy of neutralization. It's not next topic, but next subtopic. So under enthalpy of neutralization, you're going to say that the reaction between an acid and a base is going to be introducing this. We're going to say that the reaction between an acid and a base to give a salt and water is going to be called enthalpy of neutralization or enthalpy of reaction. The neutralization reactions are always going to be exothermic. So whenever you are defining enthalpy of neutralization, it's always going to be heat given out, not enthalpy change. Once you write enthalpy change, you are going to be marked wrong. So examples of such reactions are going to include the following. When you're having any acid reacting with a base, that's called a neutralization reaction. We form a salt and water, and always heat is always given out. Also, for example, if you're having ethanoic acid reacting it with sodium hydroxide, you're going to form sodium ethanol together with water, a salt and water, and always the heat change is going to be exothermic. So you're going to say that, therefore, we are going to define enthalpy of neutralization as the, cross out this. Enthalpy of neutralization is going to be heat evolved when 1 mole of the hydrogen ions reacts with 1 mole of the hydroxyl ions to form 1 mole of water. It's as simple as that. Heat evolved when 1 mole of the hydrogen ions reacts with 1 mole of hydroxyl ions to form 1 mole of water. Now some people go ahead and further advance this definition, which is okay, by saying that it evolved when 1 mole of hydrogen ions from an acid reacts with 1 mole of hydroxyl ions from a base to form 1 mole of water, and that's also totally fine. So you're going to note that the enthalpies of neutralization of strong bases and strong acids and vice versa are usually high and constant because the acids or bases are completely ionized to give high concentrations of hydrogen ions and hydroxyl ions. However, the enthalpies of neutralizations of weak acids are going to usually be low and not constant, and the reason for that is because the neutralization of the weak acids or bases, some energy is first used up in terms of energy is used up to make these weak acids ionize. So since some energy is used up, you'll find that they are not going to be fully ionized in solution. So we're expecting the enthalpies of neutralization of strong bases and strong acids to be far greater than those of weak acids and weak bases. And the reason for that is because for weak acids and weak bases, energy is required for them to ionize, which is not the case with strong acids and strong bases. So we're going to be looking at the experimental determination of enthalpy of neutralization, and here we're going to start with a known volume, which is going to be V centimeters cubed of an acid, of a known concentration of an acid, which is going to be m molar hydrochloric acid, is going to be placed in a plastic cup, a plastic beaker, and its initial temperature, which is going to be denoted as T1 degrees Celsius, is going to be noted. And then an equal volume of the same concentration, m molar sodium hydroxide, is also going to be placed into another plastic beaker, and its temperature, or its initial temperature T2, degrees Celsius is going to be noted. Now you should note that when you are noting these two different temperatures, the thermometer must be thoroughly washed or thoroughly cleaned between when you're removing it from the beaker of hydrochloric acid to a beaker of sodium hydroxide. You must first make sure that the thermometer is thoroughly cleaned and dried properly between the readings as a precaution. So the other step is going to be the hydrochloric acid is going to be transferred into a container having sodium hydroxide as quickly as possible, and then the maximum or the final steady temperature, which is going to be denoted as T3 degrees Celsius, is going to be noted. So the assumption that are going to be made as we are treating these results is that the density of the solution is going to be the same as the density of water, which is going to be 1 gram per centimeter cubed. And then the specific capacity of the resultant solution is going to be taken to be 4.2, which is the same as water. So we're going to say that therefore each change is going to be given by total mass of the solution times specific capacity times temperature change. But let's first note down the different components. We already have this one, which is 4.2. Let's note the temperature change. Now for us to get the temperature change, we get the final temperature after combining the two, and then we less the average temperature. So delta T is going to be equal to final steady temperature after combining the acid and the bases was T3, and then we less the average temperature, and we get the average temperature by adding the temperature of the acid together with the temperature of the base and then dividing by 2, and that is what is going to give us our temperature change. And then we deal with the mass of the solution, and for us to get mass of the solution, we are going to first get the moles of sodium hydroxide that reacted with hydrochloric acid. Now since they're the same, since they're of the same concentration and same volume, we are going to say that but moles of sodium hydroxide are going to be equal to moles of hydrochloric acid that reacted, and therefore this implies that moles of water that are going to be formed is going to be V divided by 1000 times A, and this expression is because we use the known concentration of M molar. So that means that 1000 contain M moles. Then what about the volume that we used, which was V? Is going to contain how many moles? So after simplifying, you're going to end up with 0.001 VA moles of the water that were formed. Since mole ratio was 1 to 1 to 1, if you react hydrogen ions together with hydroxyl ions, you are going to get 1 mole of water. So since all of them are having mole ratio of 1 to 1 to 1, they are going to have the same moles that reacted and that were formed. And therefore, for us to catch it for the enthalpy of neutralization, you're going to say that therefore those moles of water are going to be formed after liberation of heat, and heat is going to be given by the total mass of the solution times specific capacity times delta H or delta T in terms of joules. What about 1 mole? Because in enthalpies we are focused at 1 mole, heat given out by 1 mole. So what about 1 mole of water is going to liberate which kind of heat? So you're going to divide through by 0.01001 VA. And after that, for us to convert enthalpy of neutralization, make sure that you put a negative, because always enthalpy of neutralization is negative. So a negative in front of this bracket, and for us to convert these joules per mole, you can either divide through by 1000 or you can leave it the way it is. If you divide through by 1000, you put here kilojoules per mole. If you leave it the way it is, you leave it in terms of joules per mole as the enthalpy of neutralization of that specific salt. So we're going to look at the example of such question, or the way we can approach such a question about enthalpy of neutralization. So first, we got a volume of 250 centimeters cubed of 0.5 potassium hydroxide at this temperature and put in a beaker. And then we got an equal volume of 0.5 molar hydrochloric acid at the same temperature, and then the final temperature was found to be 15.4 degrees Celsius. Now we are going to be required to calculate the enthalpy of neutralization, assuming that the specific capacity is the same as that of water to be 4.2 joule per gram per Kelvin. So we're going to start by getting mass of the solution. But mass of the solution, remember that we're having 250 centimeters cubed used. So what you're going to do, the way we get mass of the solution is that we get total volume. Total volume, we multiply it with density, which is 1. We assume that is the same as water. So I didn't include the multiplied times 1. The total volume of the solution was going to be volume of the base used plus volume of the acid used. After that, after getting total volume, you convert it into mass by simply getting volume times density. We assume that density is 1 gram per centimeter cubed. So we get 500 grams as our total mass. And then we are going to get temperature change simply by getting the final steady temperature, and then we less the initial temperature. Remember that the two of them were carried out at 12 degrees Celsius, and it was the only temperature given. So it's going to be 15.4 less 12, so that we can get 3.4 degrees Celsius. So for us to get heat change is given by total mass of the solution times specific capacity times temperature change, which is going to be equal to 500 times 4.2 times 3.4. Putting everything in the calculator, we are going to end up with 7,140 joules of heat. Now we want to see these joules of heat were given out by how many moles of the solution. So you're going to say that, but moles of potassium hydroxide are the same as moles of hydrochloric acid that reacted, and therefore we only pick one. So since we used 250 centimeters cubed and we had a concentration of 0.5 molar, we are going to say that 0.1000 centimeters cubed contains 0.5 moles. Then what about 250? And you're going to end up with this expression. And you're going to end up with 0.125 moles to be formed. Since mole ratio between potassium hydroxide and hydrochloric acid and water is going to be 1 to 1, you pick one reagent that you're going to use. So I'm going to use water. So I'm going to say that because they're going to have the same moles. So I'm going to say that 0.125 moles of water were formed after liberation of the heat that we calculated. Then what about 1 mole? Since enthalpy of neutralization is always got in 1 mole, it's going to be this divided by these moles, then times 1, which is here. And you're going to end up with an enthalpy of 57,120 joules of heat. So for us to convert it into kilojoules, I say that you divide through by 1,000, so that you put it in the standard units. So therefore, enthalpy of neutralization is going to be negative. We say that this negative must be there because enthalpy of neutralization is negative. So negative 57 after dividing through by 1,000, 57.12 kilojoules per mole. And I said when you're writing kilojoules per mole, you have to be very careful. K is small letter, J is capital letter, and then the others are small letters. So here we are going to briefly talk about heat of precipitation. And heat of precipitation, you're going to say that this is going to be the heat change, which is going to occur when 1 mole of an ionic compound is precipitated from a saturated solution of a sparingly soluble salt. And this one is not highly examinable because this definition is going to be handled more in details under ionic equilibria, which are the videos that are already uploaded here. So make sure that you check them out under the playlist of physical chemistry. Now, alternatively, enthalpy of neutralization can also be determined by a graphical method. And what you need to know here are the following steps. So first, a known volume of a base is going to be put in a plastic cup, and a known volume of acid is going to be added to the base at intervals of a given volume, for example 5 centimeters cubed, using a braid while taking the note of the temperature at each interval. Whenever you add a specific volume, you take the temperature present at that interval. And the graph of temperature of the solution or temperature rise against volume of the acid being added is going to be drawn. And doing that is that you're going to get a graph in the following shape. So the x-axis is going to be in terms of the volume of the acid being added to the base in terms of centimeters cubed. And also this one can either be in terms of temperature of the solution or temperature rise of the given experiment, or at various time intervals, or at various intervals of addition of the acid. So what you do to get the maximum steady temperature, which is going to be enthalpy of neutralization, is that you extrapolate. You extrapolate your graph by getting two plotted points. It's like drawing a line of base feet. From this side, you get 2 plotted points that are in the same line. That are near the peak, and then you extrapolate them using a dotted line. Also this side, you get 2 points that are also on this curve. You also get your ruler, and then you extrapolate them. Now the point of intersection is what is going to give you the maximum volume of the acid added together with the maximum temperature, and your maximum temperature obtained here is going to be your enthalpy of neutralization. These are the questions that are going to be trying out to test your understanding about what you have covered. And I say that try to discuss with your friends. Make sure that you approach your teacher in case you have failed to find any of the allocated answers. So try out these numbers, discuss them, try to share the questions to your friends. And if you all get confused, try to share the videos to your friends so that you can all understand differently and discuss all the issues differently. That's the only way you're going to be good at this subject. So pause the video and you take the questions. And that's it for thermochemistry. This video and notes have been compiled by Wolfgang Yusuf and advised by Wolfgang Yusuf. Your advice, share the video to your friends and study as a group. Make sure that you engage in a lot of discussions before you sit for your final papers. See you in the next video where we are going to be starting structure and bonding, still uploaded on this channel. So make sure that you go through all the videos and you watch each of them for you to perfect the concepts. So see you in the next video.